Suppose now we have the function f of s is equal to the square root of the quotient s squared plus 1 divided by s squared plus 4. And we wish to take the derivative of this function. Well, first, let me manipulate this a little bit. That is a square root. And as I'm sure you're aware by now, that is usually easier to differentiate if we write it as a power. So we have s squared plus 1 over s squared plus 4 raised to the 1/2 power. So now when we take f prime of, sorry, not x, s, there we go, f prime of s, we have something to the 1/2 power. So the power rule tells us that is 1/2 times that thing to the negative 1/2 power. But that thing is more complicated than just our variable, so the chain rule tells us we have to multiply by the derivative of that thing. Well, what is the derivative of that thing? Quotient rule is what we need to use there, right? We'll have the derivative of the top, which would be 2s, times the bottom, s squared plus 4, minus the top, s squared plus 1, times the derivative of the bottom, which is 2s. And this is all divided by the bottom squared, right? So let's start some algebraic simplification, because this is kind of a mess. I've got the 1/2. Let's leave that alone for right now. Not sure. Yeah, I don't see any harm in doing this. We have a negative 1/2 power, which means that this is actually a fraction. It's a reciprocal of this fraction. So let's handle that negative exponent by switching the numerator and denominator. We're basically bringing that negative 1 power inside to the numerator and denominator to switch those positions and make this a positive 1/2 power. Let's distribute in the numerator there. We have 2s cubed plus 8s minus 2s cubed minus 2s, it looks like, all divided by s squared plus 4 squared. Now, of course, hopefully you see we have a 2s cubed minus 2s cubed. Those add up to 0. So let's see here. We have 1/2 times this fraction here. Now looking at this, we have an s squared plus 4 squared and an s squared plus 4 that's in this 1/2 power. Let's take this 1/2 power and kind of apply that to the individual pieces, right? We have a fraction to a power. We can apply that power to the numerator and denominator individually. So it's s squared plus 4 to the 1/2 divided by s squared plus 1 to the 1/2. In the numerator here, we are left with 8s minus 2s gives us 6s. Dividing that by s squared plus 4 squared. Okay. Now, a few things going on here. We see, let's go ahead and combine these fractions and simplify what we can. This 2 is going to cancel with the 6, leaving a 3. So we'll have a 3s in the numerator. Down in the denominator, there's this s squared plus 1 to the 1/2 power. We have s squared plus 4 to the 1/2 in the numerator, s squared plus 4 squared in the denominator. That partially cancels, leaving us s squared plus 4 to the 3/2 in the denominator. So that took care of that, and I think all we're left with then is the 3s in the numerator, and that looks like about as far as that thing goes. So make sure that you're still comfortable with all of your algebraic rules in terms of dealing with fractional powers, fractions, rational expressions, all of that kind of business. We often want to simplify things as far as possible. There's a little bit of work involved, but this final expression I've boxed is a whole lot easier to work with than this first thing we got, right? Technically, where I have f prime of s equals this line right here, I mean, this is the derivative. That's the end of the calculus, quote unquote. That's the full derivative there, but this is very unwieldy and would be terrible to work with in most applications. So we want to simplify that down as much as we can. Now what I did here, putting this 1/2 into the numerator and denominator separately, suggests an alternate approach to the beginning. We could have done that at the beginning here and taken this as s squared plus 1 to the 1/2 divided by s squared plus 4 to the 1/2. And then the first thing you would do is the quotient rule, and inside the quotient rule you would have some chain rule to apply. I don't think I've worked through that recently, so I don't remember if that's any easier or harder. You could try that out if you wish and see how that goes. You should still be able to algebraically simplify it to something equivalent to this. But, yeah. So here we had a case where, again, we had to combine the chain rule with another rule. In this case, we first had the chain rule because the outermost function was a square root, so we had to deal with the derivative of that square root first. And it was one of the inner bits. It was after we applied the chain rule, in the process of that we find a quotient rule to unpack.